Okay, so dense objects move towards where the medium is denser. Yep. And then less dense objects move towards where the medium is less dense. Yes.
Okay, so this one, I think we can agree this is definitely part of the hypothesis. We'll keep that.
Let's say we had a medium that had the same density. If that, I'm not sure if that's possible, but let's just say we did. I still think less dense would rise and more dense would go down, because relative density is the difference between the object and the object's density and the medium's density. To me, that's how we've got the gradient to begin with. So basically, in nature, the reason that more density is down and less density is up is because you've got a medium, and less dense is up and more dense is down. So that's kind of where the gradient come from to begin with. So if you imagine just everything, just imagine one medium, and then you had all objects of different densities, or all gases in this medium of different densities, and then just imagine it sorted itself out so that more dense was down and less dense is up, because more dense in the medium down, less dense in the medium up. You'd end up with a gradient eventually anyway, and that's where I think our gradient came from.
And okay, so this one, no. I think you were a little bit unclear about that exactly, but one thing was clear was we cannot count on this. It sounded like you thought that maybe sometimes this was an effect, but let's say that in general, this is not the case. Maybe I'll come back to this discussion of how the gradient is involved, but in general, the gradient is not part of the relative density hypothesis.
The density of the entire object is what counts. Yes, the density of the entire object, not what it's made of, not its individual materials, the overall density of the object.
The entire object is correct part of the hypothesis.
The next one is the object must be in contact with the medium for this effect to occur. Yes. I've told people before that it needs to be immersed in the medium, it needs to have contact. I did actually describe it myself before as a contact force.
And yes, it must be a contact force. So we keep this. Let's just get rid of that one clause. That just brings us down to this. This is our new relative density hypothesis. Now, that actually, believe it or not, brings me full circle back to suggesting this as an equation to describe your hypothesis. This is the relative density, and the amount of force acting on the object will be based on the relative density between the object and the medium. The amount of force is also based on the size and volume of the object. Larger object, more force. More density, more force. Negative density differential, and the force will be in the opposite direction. It will go up.
Density gradient is the cause. Not really, no. The relative density is the cause. The density gradient is not the cause of objects moving. I'm not sure whether we can have a container with the same density all the way through, consistent density. But if we could, as I've said, more dense will always go up. More dense will always go down, less dense will always go up. You don't necessarily need a gradient for that to occur.
So next I show this, the big question. I was thinking that this was going to be the foundation for the experiments that we could conduct and prove once and for all whether this was correct. But this was wrong. This was based on a straw man. Thank you for correcting me. No, there is no claim in general that the density gradient is the cause of the way things move in general. Typically, you have described that even with no density gradient, the dense things will go down and the light things will go up, and that will create the density gradient.
Less dense down, more dense up than the medium. That's why we've got a gradient today, where we live. So yeah, less dense will always go up, more dense will always go down.
So what I'm hearing you say is that the density gradient is not the cause of the way things moved. It is in fact the effect that the dense things went down, the light things went up, and that created the density gradient. Therefore, this is not our hypothesis, and we're going to need to go back to the drawing board.
It's a really good exercise to try to fight your own internal biases, to decide before you do the experiment what your response should be to the null hypothesis.
Well, I agree with that. I think to me, I think we need to decide what the experiment's going to be before we can come up with a hypothesis. So for me, depending on the experiment being conducted, if you could articulate an experiment to me, I could give you my hypothesis for what I think would or should happen. Or
what I want to do with these hypotheses and experiments is to determine whether this relative density idea is correct or the competing idea, which of course, we've heard of Newtonian gravity. That's got to be on the table for our competing ideas. How can you tell which is correct? If there's no difference between them, then it doesn't matter which one is correct, or we can't tell. We certainly cannot tell if there's no difference. So we have to isolate something that is a difference between the two competing ideas, and then we can test specifically for that difference. So that's what this whole exercise is about. We're trying to figure out something that's different. In what way is relative density different from basic bog standard Newtonian gravity like they put in the physics textbook? For example, we could just do Riley's egg experiment, right? We could put an egg in some water and say, oh, look, it sinks, and we can add some salt and say, oh, now it floats. And then we could just declare that that validates our hypothesis. And we say, yes, that proves relative density. The problem with that is that the egg experiment is completely compatible with the alternate hypothesis of Newton's gravity. Newton's gravity also predicts that the egg will rise if you add salt to the water. So we didn't accomplish anything. We were not able to tell the difference using that experiment. We need a way to tell the difference. And with this one removed, with the density gradient part of the hypothesis, if I remove that, which, I've crossed it out, I no longer have a difference. So far, we're back to this. We're back to the relative density hypothesis with these 3 points. And the problem with this hypothesis, with these 3 points, is simply that there is no problem with these 3 points. There's nothing wrong with it. It's correct. Ask any physics teacher, ask any physics student. This is correct. There's nothing wrong with any of this. This is bog standard physics that is taught in schools today. So if you want to insist that relative density is different from gravity and different from buoyancy as it is currently taught, then we're going to need to go beyond these simple 3 points.
like I could give you a hypothesis beforehand and we could do the experiment, and then there could be a factor in there, a variable or something in there that changes the outcome kind of thing. So let's say, something always happens, and then we do an experiment, and then we do this experiment in a way that adds other forces or adds other components, other parts, other influences that can influence and change the effect or what we observe. And that, I wouldn't really say that's a fair test then of the hypothesis, because we need to control it so that there are no other forces or influences becoming a bigger factor than the relative density.
You make excellent points right there. In fact, I have just released a video about the scientific method and what it is not, very much what it is not, and some of the reasons why it is not so strict as you sometimes hear. And one of those reasons that I highlight in there is that there are unexpected things that happen in experiments. And so I always encourage everyone to think about what you should say if your experiment invalidates your hypothesis before you get your results. Because after the results come in, it can be really hard to accept them. But at the same time, don't go thinking that your experiment is so perfect that a single run of a single experiment completely blows your whole theory out of the water. There may be other variables, right? There may be other things you haven't even thought of. What I would say, if the experiment goes in a way that I do not anticipate, I think the first thing I would say is interesting, and I would say it in my very best Jaron impersonation, because that is exactly the right reaction, is to be stunned and shocked that the results are surprising. So you say interesting, and then you say this does not seem to match my hypothesis. We'll have to go back through the experiment, look for mistakes, ask other people to help us find mistakes, that kind of thing, before we officially declare that any single experiment is, has completely debunked everything, right? That's not really how we do it. We say, well, that experiment didn't work out. So either you've got a mistake here or your hypothesis is wrong, right? Always leave a little room for that mistake. After trying to edit this, I decided that the best course of action was to make the mini video on the density gradient thing. And that I'll put a link right up there for anyone who's catching this one first. And that really addresses this first question. And then after that, I summarized the rest of it with these just 3 questions. Let's boil it down to, I have 3 questions for you that if you could answer, I will understand you better. And then maybe together we can pursue those to see what are the differences between gravity and relative density, and differences mean testable. We can actually find out what the truth is. Okay, so number 1, does the density gradient ever cause objects to move in a direction that's not just dense goes down? The reason I'm asking is because we might be able to test for that. If you predict that the density gradient can make objects move in a way that is not predicted by standard gravity, we can do that experiment and prove once and for all that relative density does this, or relative density does not do this, right? If we can pin that down, we can make an experiment. Okay. Number 2, you've agreed that generally when there's no gradient, dense goes down. So if that's the case, and we absolutely agree that is the case, dense things go down with no gradient, then don't you agree that simple statement means down is a special kind of direction? Down is unique. Up and down, this axis of up and down, is different from every other direction because it has that special property that dense things go down. I think that makes down special. Do you agree? Doesn't that mean that down is a special direction? Let's just start with that. Okay, and number 3, if you have any ideas, do you have any ideas about how to differentiate between gravity and relative density? Ideally something that we could test, but let's just brainstorm. What are all the ideas, all the things that you think make the idea of relative density different from the gravity that they taught you in the textbook? I mean, I've got some ideas, and I know we've heard from everybody else all of their ideas, but what do you think makes these things different? And then let's take your list. Let's take your list. Maybe I'll add some things to the list. We'll make a big list and then try to think of ways to test for those, right? And then that's how we can get closer to objective reality, is we find differences and then think of ways to test for those differences. Great talking to you as always. Looking forward to some responses later. Okay,